hope you've all had a chance to visit the Leopold's review section for past week and for this week, because it's kind of important to make the connection between the long run and the short run. And for the rest of this course, we're talking about the short run. We're talking about how impulses get transmitted into effects, into propagation, into the business cycle. And we started with the graphical analysis, and today we'll try to move into a mathematical version of the same idea. And this vanilla version is basically just to show you that you can generate, using this idea of Slutsky, random shocks accumulate into effects that look like a cycle. An irregular cycle is the way that macroeconomists think about the business cycle in general. And therefore, we can't just talk about a shock. There are different types of shocks. There's demand shocks, there's supply shocks. Among the demand shocks, there may be a shock to monetary policy. There could be a shock to fiscal policy. There could be a shock to consumer sentiment. And the model that we've dealt with until now is very generic, and that's we'll keep it for the next hour and a half. And then after that, it gets more specific and more detailed. And if you take more advanced courses in this area, you'll do more about this. So I'm going to try to teach you a few basics about what were called difference equations and how we think of this Slutsky mechanism, this impulse propagation mechanism that's at the core of what we do in this course, in macro in general. I call it the bread and butter of modern macroeconomics. Okay, so it's difference equations. Current values depend in some way on the past, and that's because of some economic model that we think we understand. And then the shocks are not inherently foreseeable. For example, we observed this year. This year was a complete surprise. This past year, 2022, was a complete surprise to everyone. And the effect of that surprise is what we're sort of living through right now. Okay, so I associated with the great Russian mathematician and economist Eugene Slutsky, but of course it's also been attributed to other people, and it's, again, what we do throughout the field. I'm going to try to give you a cookbook approach to solving second-order difference equations, because that's a fairly standard way of summarizing dynamic behavior. Second order means the current value depends on its lagged value and another lagged value, two lagged values. And in quarterly data, that seems to be a pretty good way of capturing what's going on. So if you actually like econometrics, you could go out and try to estimate some lag dependence, and you'd find generally the second order is a pretty good approximation. It turns out that a lot of our models will point to a second order difference equation, so it's a starting point. More complicated analyses, you need a computer. You really need to throw the thing at a computer and let the computer solve it numerically usually, and then produce some summary statistics and thinking about the way the model behaves. And if you think about it, we had these curves shifting. That was the impact. And then we thought, well, what happens after that? Well, what happens after that is exactly what the difference equation system would try to predict. Okay, so at the end of this hour, I'm going to try to show you that there are a couple of special summary statistics that summarize how these dynamic systems behave. And we call that the characteristic root of the system. So depending on the order of the difference equation system, there'll be different number of characteristic roots. And what those things look like will be kind of a diagnostic for how the model behaves, especially if it's explosive or not explosive. So some models, you shock them, and the thing just sort of goes out of control. That's not what we observe in reality. So we'd like to have a discipline in our model that would prevent that from happening. So that's one kind of basic idea. The other is, how does the model converge? Does it converge in a loop or in a cycle, or does it converge monotonically to its long-run value? Okay, in some sense, we've seen a little bit of that in the growth theory. We didn't have cycles yet. Right? We had pretty much monotonic convergence to a long run. So let's review what we did last time. Last time was easy. We were thinking about pictures, right? Supply and demand. Thinking about the cycle as a deviation from some long-run trend, and those deviations are caused by supply shocks or demand shocks. Usually most of us think about demand shocks. We think about the recent corona crisis. It was mostly a demand shock. People stayed home, didn't want to go shopping, and On the other hand, there's a feeling there may have been some supply shock because workers didn't want to work. They were scared of going to work, or they were staying at home, weren't being productive. So it was kind of a combination of those two. But you can think about any sort of business cycle. Think of the financial crisis, 2008, 2009, collapse of the banking system, collapse of investment. That's a demand shock. And we saw that in the data. We saw in the United States, in Germany, in France, in Italy, we saw a decline in output and a decline relative to trend, and we saw a decrease in the inflation rate. So it's pretty easy to diagnose that kind of shock, right? And I tried to motivate that by just showing some facts. And it's not necessarily the case that inflation and output always move together in the same direction. So that would indicate that indeed we have to be a bit more sophisticated. We have to think about supply shocks and demand shocks and supply shocks. And this undergraduate model was kind of my basis for getting you interested in it. And it's a nice way of making some clear distinctions between the way an economy reacts to different events. Okay, so the recent year was really a challenge for economies, and we think we have a very good idea of what's going on, but it's not enough to tell a story. We want to have something that actually can be used in new situations going forward. So today we're going to spend a little bit more time talking about these stochastic difference equations, and it's always an implementation of Slutsky's idea. The idea is it's a random shock that we can't necessarily predict. Maybe this year we'll have peace, and price of oil will fall, and we'll be back to good old days, 2019 or 2018. That's a possibility, but I can't tell you it's going to happen. You can't either. But conditional on that, assuming that happens, what happens? That's what economics is about, trying to tell us that. Okay, so again, difference equations is the core of macroeconomic dynamics. There's dependence of current behavior on the past, current mistakes we've made carry forward into the future. So you signed a wage contract and you only thought the price level would rise by 5%, and now we've got a 10% change in the price level. You made a mistake. You worked too hard. You probably would have, if you could have rewritten your contract, you would have done something differently. Okay, so those are mistakes that may also get propagated by the system. The same thing is true of investment. Investment is conditional on an expectation. If I spend $500 million renovating these buildings across the street, that's kind of conditional as an investor that there's going to be some rate of return that will justify, there'll be some return on that investment. But if I'm wrong, right, if people just decide not to come to Berlin anymore and the students go somewhere else and study in another country or another city in Germany, that would depress the demand for the rent of those buildings, and that would be a kind of a mistake. So a lot of what economics is about is kind of correcting mistakes, and that's where the dynamics comes in. So we're going to try to think of that as an impulse response, a response of a shock. How does the shock get sort of worked through the system? And I'm going to try to motivate that now. We started with an undergraduate model, and we thought of that as kind of a demand and a supply system. And the outcome of this demand and supply is output as deviation from a trend and some inflation rate. Right? That was kind of and there's a lot of consensus on that model. I mean, you can take macroeconomics anywhere in the world and get that sort of basic insight. And we kind of know where that long-run inflation rate comes from. We know where the long-run output comes from, and we know kind of where the deviations of the trend come from. But making more sense of it is where the course gets interesting, in my view, anyway. Okay, so we started talking about this picture. So we start with a picture. And we think about what that picture is supposed to embody. This is a behavior of agents on the demand side, demand for goods and services, final goods and services at constant prices. It's kind of an easy definition of what real GDP is. Okay, so that's already incorporating the behavior of households, the behavior of firms, the behavior of government, behavior of foreigners who are importing our goods, because that's what matters. And it's also the behavior of us, consumers and firms, demanding output of other countries that doesn't go into our GDP. So it's a net, right? So for a closed economy, we can restrict our attention to C plus I plus G. We wrote down this mathematical summary of those relationships. And I tried to, Leopold is going to go through this in the coming week. This is a really stripped down version, but it's kind of getting down to the basics that we'll need to understand this dynamics, how the model propagates shocks. So the first equation is the demand curve. There's some sort of dependence of current demand for goods and services on the past, and in 2 weeks we'll explain a very, very big component of that dependence. There's a dependence on the real interest rate. Right? So the real interest rate is low, people demand more goods and services, companies invest more in equipment. That gives rise to a potential negative relationship between inflation and demand, because the interest rate in the second equation is determined by the central bank. So that's a very common element of macroeconomics. Every country has a central bank, unless you're in Hong Kong. Hong Kong is run by private banks. But in most countries, it's a central bank. And the central bank has a rule that they react. They want to fight inflation. That's the first term, C1. And the second one is C2. They want to keep output not from collapsing. So if output is low relative to trend, they stimulate. They'll cut interest rates. And if output is growing too fast, they raise interest rates. You combine those first two equations, you have really what the aggregate demand curve is in our course. It's a negatively related it's a negative relationship between output demanded and the inflation rate that we observe. Okay? And that's a pretty robust relationship. It can be shocked by D, so you can have Scholz decides to give everybody a present, 100, 200 euros. We all have some extra income and we spend it. That would be thought of as a demand shock. Holding inflation constant, holding everything else constant, more demand is forthcoming. Now, that's just one side of the scissors. Think of microeconomics supply and demand. It's the same idea. The output that is demanded in an equilibrium has to be forthcoming. So firms and workers have to combine their efforts to produce it, and they have to be incentivized to do so. And that's the third equation. And this is one of the most controversial relationships in macroeconomics. Is basically how economies respond to changes in inflation relative to the inflation rate they were expecting or had contractually embodied in their behavior. Okay, so that three elements we talked about briefly. The first element is this core inflation, this inflationary expectations. In the old days, we used to call it inflationary expectations. It's more than that now. It could also just be people writing contracts that bind a company to supply goods at a certain price for 2 years, or workers have to work for a certain wage for 2 or 3 years, and they get stuck in inflationary expectations that are no longer valid. They can't do anything about it. Okay, so that's kind of that sets the position of the supply curve. And then we've got this notion that when output increases relative to its trend, firms raise prices, workers can try to raise their wages. That would give rise to a B1 that's positive. And then all that given, there's a shift that's possible. And that shift is what we observed last year. We observed these massive increases in gas prices, for example. 500% increases in gas prices had nothing to do with the inflationary expectations or embodied inflation. It had nothing to do with output relative to trend. So that's the joker, if you like, the supply curve. And then just to wrap up the model, we add this one version of thinking about this core inflation. And I'll talk about at the end of the hour, I'll talk about what we also think about. So if you take other courses in macro at this university or elsewhere, the idea is this is the anchor that kind of sets the position of the supply curve in this diagram that we looked at. Okay, so Leopold we will solve this in the problem set. I give you an example of the problem set. The problem set is slightly different because it involves a target inflation rate. The central bank in this particular setup has a target rate of inflation of 0, just to make it easy for you to get your mind around it. Okay, but in the problem set, we think about what happens if a central bank decides to increase the target rate from 2%, that's the alleged target in the European monetary system, or the United States, 2%. Suppose they went for 5% permanently. What would happen? What if they went to 70%? What would happen? So that's kind of what this model is going to tell us. Right? The central bank permanently increases its target from here 0 to some positive. Well, we'd expect, because of monetary neutrality in the long run, the inflation rate will eventually also be that rate. Inflation rate will catch up eventually. The question is, how does it catch up? Which curve shifts first? Which curve shifts second? Which catches up? So that's really what the dynamics is all about. So I took this toy model from last week, and I just did some simple substitutions. This is what you'll do on the problem set. I expect you to do this, except your version will have a little target rate of inflation. It'll be a little bit different, you'll have a little constant to carry around through the algebra. Okay, but it's really simple, right? You take first off, you have a core inflation rate. It's based on inflation and lagged inflation, so you can substitute it out. Okay, so that makes it easy for you to get your mind around. And then you can combine it with the Taylor rule, and first difference, the aggregate demand curve takes current value minus lagged value, and then you can eliminate inflation. So you end up having the last equation. Output is dependent on past output, dependent on 2 periods past output, and a shock. Okay, we call that a stochastic difference equation. Inflation has been solved out. Okay? So is that an accomplishment? Well, it summarizes all the interesting action in the model. We can look at inflation. We can actually solve for inflation, but we have sort of an equation in output alone, and that can help us understand how this propagation mechanism works. On the other hand, these alphas are functions of the deep parameters. So no matter what we do in the next few weeks, we'll always be thinking about these deep parameters. That's the foundation of the model. And that's what makes this ASAD model an undergraduate model. It doesn't really explain very well what's going on in the background, behind the curtains. Behind the curtains are the micro foundations. What justifies the upward sloping curve or the downward sloping curve? And that's basically what those alphas are about. They're complex functions of A1, A2, C1, C2, B1, and theta. Okay? And if you know something about econometrics, you know that there's not a unique set of parameters that you can reverse engineer to get those alphas. There are many. So it's an identification problem. Theories, we have too many theories, and maybe only a couple of values of alpha 1 and alpha 2 that the data tell us about. So the challenge of our field is to try to find out what is the best model for explaining those values of alpha 1 and alpha 2. And you can see that the shocks are actually complicated as well. Look at the first. This epsilon is a mongrel. It's a mixture of many different things, supply and demand. So unless we know for a fact that supply was not active during a period, there's no a priori reason to think that the shock will have a positive or a negative effect, right? And it's the same thing we talked about with inflation. The inflation correlation with output can be positive or negative depending on whether the demand or the supply shocks were predominant. So we have a bunch of data, we have some interesting observations, but getting the right model is the challenge for us for the next few weeks. Yeah.
Did you give an intuition why the supply shock doesn't contain its lag value? What the demand shock does?
Why the supply shock is a level and the first difference? Yeah. Okay, that's a great question. The supply shock is shifting the supply of goods and services at a given inflation rate, and the demand shock does the same, but the demand shock cannot raise the inflation rate permanently. The only way you can raise the rate of inflation permanently is what? I kind of said it at the beginning. How does our model predict a higher inflation rate forever? And where do they come from? Ultimately, if you expect inflation, we learned that earlier in the course, it's not enough. What do you need for inflation to be higher in the long run? You need the money supply to be growing at a higher rate forever, or the central bank makes sure that happens by having a higher target rate of inflation. So it's the target. It's all about the target. The target is the position of the demand curve in this world. And if you have a world of fixed exchange rates, like in the Netherlands, for example, you're fixed, or Germany relative to the Netherlands, because we're all using the same currency, it's about the other guy's inflation. So the target, there's no target inflation if Croatia was fixing the exchange rate to the euro for a while, right? So when they did that, basically they just took the euro inflation rate as their inflation rate. And that fixes their expectations. But, that's for an international course. We're talking about a closed economy. The central bank has the ultimate say on the inflation rate. Right? Does everybody buy that? I mean, and that's why the only way you can get the inflation rate up permanently is to have a higher target rate of inflation. And we don't have target rate inflation changes here. It's set to 0 just to help you get your mind around this. But later on, we can do that. We can add a target rate of inflation which is not anchored. And that's why central banks are always being asked to commit to an inflation rate. Otherwise, they have no credibility. Right? So the whole discussion of leading to the European Central Bank was how can we force the European Central Bank to have credibility? It's never existed before. We're inventing something from scratch. People aren't going to trust this money. They're going to expect Weimar Germany or something. Right? Or the Ukraine in 1990. Hyperinflation. So, so we start with this this setup. A permanent shift in demand that leads to a higher rate of inflation permanently can only come from the rate of growth of money or from a target rate of inflation that's higher. And we know from our first part of the course that's the only way this happens. Right? Inflation needs an expansion, a permanent expansion of the monetary aggregate, and the only way that can happen is the central bank accedes to that and does it. Okay, so that's the bridge. All right, so this looks awful, right? This is not something you'd want to do for an exam. And I wouldn't ask you to do that, but you'd be expected to know that this reduced form, the first equation is a reduced form, expresses a very complex dependence that comes from economic theory. And this is not great economic theory. This is undergraduate, ASAD. So we're going to try to burst out of the chains of that in this course. And I mentioned this supply and demand shock come together in a way that's not, it's dependent on the model. It's going to depend on A1, A2, C1, C2. So depending on whether the central bank is really strict about inflation, C1 is really high, or whether it doesn't care, right? C1 could be very low. It's going to affect the way this model behaves. Even this model, this is like driving a two-cycle engine car like the Trabant. It'll get you there, but it's not a great way to get there. You want to have a nicer car, if you want to have a car. Okay, so the reason I do this is just to get you on the page so we know the next set of things we're going to talk about is why that AD curve is negatively sloped. What is the fundamental economic mechanism? Well, we already have a good idea. What is the mechanism for why prices don't fully reflect demand conditions? Why do people have to make expectations and lock themselves into contracts? Why does that happen? Well, there's some good economic reasons for that to happen. People don't want to pay attention to the price level every day. They have to do their business, right? They want to have fun in life, not paying attention. I mean, if you're in a hyperinflation environment, I don't know if you've ever been in one, but the people spend a lot of time thinking about the exchange rate. They think about inflation every morning. They look at the exchange rate. What's the dollar exchange rate? Got to go run to the bank and trade my increasingly worthless money for some dollars so I can secure my purchasing power. But most people don't have to deal with that. Most of us are lucky enough to live in a country where the inflation rate is low, right? So just to give you an idea of why we do this. So let's try to think about this stochastic difference equation more carefully. So we have y, think of that as deviations from the trend. Yt is a function of yt minus 1 and yt minus 2. Okay? It's a lag dependence. So I'm going to show you a little trick to help us think about that. It's called the lag operator. It's an operator. If you hit it with this L, it shifts it back by 1 period. Okay? It's an arithmetic trick, or it's an algebraic trick that will help us think about this past dependence. So watch this. I hit xt with L, and it gives it a backshift. It's often called the backshift operator in time series. It's a linear operator. So if I take this L and I hit a linear combination of two variables with it, it's the sum of the two variables with weights given by the linear combination. That's what a linear operator means. And it also means if I hit a variable twice with the lag operator, it's like the square. So the square of the lag operator is a 2 lag. Okay, isn't that cool? So 3, L cubed, L4 is the 4th lag. So think about it in the quarterly data, that'll be like the same quarter a year back. Okay? And why would I do that? Well, because if you allow me to do that, I can actually show you why this dependence is really deep. This past dependence that comes through a lagged difference equation system will give us a very rich dependence on the path. To some extent, shocks that happened many, many years ago are still being felt today. Okay, so this building was built in 1905. That was kind of a shock. The Emperor of Germany, the Kaiser, came here and dedicated this building. Does anybody know who paid for this building? Not the Kaiser. The Berlin Chamber of Commerce, a bunch of businessmen paid for this building in 1905. And it was probably a surprise that they built it. They built it. We're still feeling the effects today. And this is because this is capital stock. Capital stock doesn't disappear after one period. It hangs around for many, many periods. So it's one of the mechanisms of the propagation mechanism I'm talking about is the persistence of the capital stock, like we learned in the first half of the course. So the investment actions of 1905 are still around today. Of course, it looks a lot better than it did when I came here because it was falling apart. In 1992, this place was a dump, okay, because the GDR didn't take care of it. They didn't invest in it. But more investment, paint, call some workers in, put some stucco on the outside, and it looks pretty good now. You're very lucky to be here. Other cohorts were not so lucky. Okay? Why am I telling you this? Because you can express a lot of this backward dependence using the lag operator. And I'm going to give you an example. Here's an example of an AR1 autoregressive first-order difference equation. Remember, I showed you a second-order difference equation. This is a first-order difference equation, right? So this alpha here less than 1, so the thing has a certain stability to it. If you shock it, it's going to return to its initial condition eventually. And I'm going to shock it with epsilon. Epsilon is a independently identically distributed random variable. So it's like Slutsky. Okay? And you start with y0. So that was the condition before the building was built here. I can use the lag operator to write this expression like that. Right? So I've got yt on the left-hand side, I've got yt on the right-hand side. This implies that the past, the infinite past, has an effect on today's value, in addition to the current shock. So the current shock gives us the jump of today, but all the past is just an accumulation of the lagged something. And that lagged something is exactly previous realizations of this shock. That's the Slutsky idea. We can show this formally. One way to show it is just recursively substituting. Okay, that's trivial. You should all be able to understand that without even me having to stand up here and talk to you about it. Right? You just lag it by one period and insert that in the current period, and then you do that again and again and again, and there's no end. Okay, so this is what we call recursive substitution. So what do we get as a result? We get an initial condition going S periods into the past. That could be 1904. And then we've got all these different shocks that have happened since 1904, 1905. That may have been the building this thing. And then we've got another shock. Then we had World War I, and we had World War II. And what we have today is basically accumulation of those shocks. The stability of the structure is the presupposition, of course, for this all to work. But as long as the alpha is the same as we go through time, we have a moving average an infinite moving average if we push it back far enough. But if we push it back to S periods in the past, we have a moving average of the intervening S+1 shocks. Okay, so that's kind of what macro is going to be. But, you know, that's, if I push that back far enough, the initial condition won't matter, right? Because if the initial condition is holding the thing down, but if we keep pushing it back, eventually the weight applied to that initial condition will go to 0. So literally, Slutsky was right. In some deep sense, what we're observing today is accumulation of a lot of randomness over time. And that's kind of one way of thinking about macro. The other way to do this is to actually use long division. Okay, so I mean, if you remember in high school or hopefully in grade school when you learned how to divide 5 by 7. Remember doing that? Okay. Well, 5 divided by 7 is not a round, easy number to express. It's a rational number, but it's kind of weird, right? So you have to write it down. You probably did this when you were in 3rd grade or something. Maybe 1st grade, probably 7th grade. I don't know. We can do the same thing with a lag operator, and you can get the same outcome. So this is kind of an aha moment for a lot of people. We can use what's called long division. Okay, so take 1 minus alpha L and divide that into 1. Well, it goes in 1 time, leading term, multiply 1 times 1 minus alpha, subtract that from 1, what do you get? Alpha L. How many times does 1 minus alpha L go into alpha L? Alpha L. Subtract alpha L minus alpha squared L squared from that. So you eliminate the leading term and you get alpha squared L squared. Repeat. Repeat, repeat, repeat. You get the same type of lag dependence on the, as far back as you want to go back, but infinite moving average, it's an infinite geometric moving average of these shocks. This is a very simple example, obviously. Okay, but you see the logic? You can use long division to prove effectively or to demonstrate that this recursive relationship can be expressed in that way. Okay, so that's kind of an interesting fact. Kind of going to motivate our macro model again. We can also push it a little bit. We can push to a harder example. But let me just say one thing. It does presuppose that alpha is not too big. Alpha has to be less than 1. Otherwise, this doesn't work. Makes sense, right? If alpha is greater than 1, the thing will explode. The accumulation of random shocks that accumulate in a way that doesn't deteriorate in any way, that doesn't get depreciated, like the capital stock, right, will eventually explode. So kind of an unpleasant result. We want to have a stability condition imposed. The obvious stability condition for this simple AR1 is that alpha is less than 1 in absolute value. It could be greater than -1. It could be between 0 and -1. And it would still be stable. It would be kind of strange looking, but it would certainly still work. Okay, so it's kind of an intuition for stability. What if it gets more complicated? What if we have an AR2 system? Look at this. This is exactly what we had before. AR2 would have 2 lags, L squared. Okay, can you do this? Yes, you can. It's kind of ugly. It's ugly. But let me just show you how we get there. We do the same trick. We take that equation, we write it using the lag operator. Now it's got a polynomial in the lag operator. It's a second-order polynomial. What we had before was a first-order polynomial. Now we have a second-order polynomial in the lag operator because it's got L squared in it. Okay? Under certain conditions, we can invert that too. And there are 2 ways to do it. The dumb way, the way I did it before, recursively, that's a mess. You don't want to do that. Nobody wants to do that. Okay? You could also use the long division method, but the logic is the same. We've got a complicated moving average of the past values of epsilon. That's what I want you to remember. The inversion of this polynomial in the lag operator induces a very complex dependence. It's not trivial. You can have all sorts of, I'm going to show you in a second, you can have waves. You can have monotone convergence. One shock, that's what we call an impulse response, and you watch how this one shock plays through the system. And that's all determined by this alpha 1 and alpha 2, the model's economic structure. It's still a moving average. Okay? We can show that two different ways. The first way is absolutely stupid. You wouldn't do that. Recursively substituting, because you'd have to track all those complex products of alpha 1 and alpha 2. Well, you're going to have to do that anyway, but I'm going to show you the easy way to do it. Okay, so let's just try this. Let's try this hard way first. Let's try the long division. It's nasty. It works. You can do it, but it requires a lot of pencil and a lot of patience. You don't want to do that. But I want you to remember that if you look carefully at this thing, what does it look like? It looks like a polynomial in the lag operator now acting backwards on this epsilon. So it's a complicated lag structure of lagged shocks. We can do better. We can factorize it. The first term is a polynomial in the lag operator. We can write it as the product of 1 minus lambda 1 times L and 1 minus lambda 2 times L. And lambda 1 and lambda 2 are defined as the sum makes alpha 1, lambda 1 plus lambda 2 equals alpha 1, and minus lambda 1, lambda 2 is equal to alpha 2. That's in high school. I learned that when I was in high school. Factorization. That's how you solve complete the square, solve a quadratic equation. Okay? But look at that. Why would I do that? Well, it turns out that 1 minus lambda 1 and 1 minus lambda 2 have the same logic of inversion that we had before. We can do that much more easily. You can invert them separately. The only thing we have to worry about is whether these lambda 1 and lambda 2s are big or small. If they're big, that could be a problem. If they're big in a way that I'm going to explain to you, that could cause instability. Remember, I'm always worried about instability in my macro model, the thing blowing up, right? That's the problem. So we're going to require that lambda 1 and lambda 2 are small in some sense. Before, I required that alpha was less than 1 in absolute value. So it's a similar logic, but it's a little bit more complicated. It's going to involve an absolute value of a number which we call the modulus. So that's a word you have to remember, okay? So look, if I can do that, if I can write this inversion in a factorized way, I've got two individual inversions, because the inverse of the first term is equal to the product of the inverses of the second. And I can think of each one of those as hitting the shock. So I get the geometric moving average, but I get it twice. I get a convolution. So that looks really, really complicated, but it's not. It's easy to formalize, and it looks so easy because if I understand the behavior of lambda 1 and lambda 2, I understand the behavior of this system. So this is often called the characteristic root, or and you'll see later, it's in a similar way, in a matrix form, it's the eigenvalue of the system. It's stability. So we're going to have to stare at lambda 1 and lambda 2 for a while. First off, I can solve for them. If I know what alpha 1 and alpha 2 are, I can solve for lambda 1 and lambda 2. You can do that. You should try to do that tonight. You'll have to use the quadratic formula to do that, because it'll involve solving a quadratic formula. But that's the cool part, because it gives us it opens new vistas in terms of what the dynamics can look like. The dynamics can have waves, The dynamics can have monotone convergence. And that's why Slutsky was right. Even if I shock it once, I can get wavy reactions. But if I shock it every period, I'm really going to get some interesting action. Okay, so if I do the factorization, we see that it's a product of two inversions of 1 minus the respective characteristic root. And then if you multiply those out, you can see what happens. We get this very, very elegant looking product of different powers of lambda 1 and lambda 2. It's called a convolution of these infinite order polynomials in the lag operator. Okay, so that's kind of that basically tells us that if I shock this system in period 0, I'm going to get a reaction into the infinite future. It's going to be damped away or disappearing at some point, but it will always be there. We're still hearing the noise of the 100-year war in Germany. We are. If you look at it, look at the villages in Germany that were Catholic, Protestant, fighting each other. I mean, when the Turks were about to take Vienna in the 17th century, this is kind of, we still hear the resonation of that today. It's one way of thinking about it. Economics is all about things that happened a long time ago that are still bothering us in some sense or affecting our lives. It's kind of the way it works. Okay, so that sounds really philosophical, but that's the way it looks from our perspective in macro, the impulse response function. So we can write this as a way a model responds to a one-period shock. In some sense, y is a sum, it's some infinite sum of these shocks going off into the past. You can think of this as you should not think of this as a structural model. This is a reduced form model, but it's still a way of expressing intertemporal dependence of variables in macro. And if we do identify the shock and say this was a demand shock, then we can look at this adjustment path through time and call that the effect of a demand shock. So I put a word here that sounds a bit terrifying, but these lambdas, I told you these lambdas are not just, they're not just normal numbers. They can also have complex conjugate form. And that means that we have to, again, dust off the high school algebra and remind ourselves that there's a possibility of having a more complicated expression than just a real number that we encounter in everyday life, which is a complex conjugate number. So we have to remind ourselves what that is. But let's get there first. Again, thinking about this univariate macro case, inverting the formula, we get this set of coefficients. So think of that as the impulse response. This sequence of coefficients that summarize the reaction to a unit shock. Okay? So to get there, we have to solve this difference equation. We just solve it. Right now, we just wrote it down. We have a reduced form yt, depending on yt minus 1 and yt minus 2, and we've got this potential shock that we'll call it epsilon 0. Think of this as a constant. Just think of this as a constant. To solve this, we need a function of time that only depends on the shock and alpha 1 and alpha 2 without any lags. So we want a function of time. And to solve this, if we solve it, we'll have the object we're looking for. We'll be able to describe the reaction of the system. We'll be able to describe its stability properties and how long it takes for a lag, how many lags it takes for half of the shock to be dissipated, etc. Okay, so we're going to use a little bit of Cookbook now. So I'm going to show you, just like we had the Hamiltonians, it was kind of ugly, but it's really helpful, extremely helpful. There's a Cookbook way of solving difference equations. So if you can remember these steps, you're fine. And then you can see why this is a useful way of proceeding, because you'll understand why we like to stare at these lambdas. These lambdas are incredibly important for describing the stability and the properties of the of the dynamics. Okay, so let's take yt as a function of once lagged and twice lagged values and this constant. So think of that as, if you like, think of it as a permanent shock. Permanent shock, maybe an increase in the inflation rate, the target inflation of the central bank, whatever. So step one, what happens when all the dust theoretically is settled? To what value does y converge? And how do you figure that out? Yt equals yt minus 1 equals yt minus 2. Right? That's the steady state. Okay, so try that. Yt equals yt minus 1, yt minus 2 is equal to yp. Call it yp. What's the value of yp? It's that. It's epsilon 0 minus, divided by 1 minus alpha 1 minus alpha 2. It's the steady state. So all the dust settles. What is y? It's yp. That's called the particular solution. It could also be 0. If epsilon were 0, then it would be 0, but that's not interesting. Okay? Step 1. Step 2 involves invoking what I showed previously called the superposition principle. If I know that one solution is a solution to a difference equation, I know that the other is a solution, then I can add the two together, and that's a solution to the difference equation. Okay, so if I know that the particular solution is a solution, then y minus yp must also be a solution. So I need to find out what y minus yp is. Well, doesn't y minus yp sound like the deviation from the steady state? Isn't that what we were looking for, the business cycle? We're looking for the deviations around the long run. So call that the homogeneous solution. Why is it called homogeneous? Well, if you multiply that solution by a constant, it doesn't change the solution. It's the same. It's scalable. Think of the yp as the location, and the yh, the homogeneous, is the additive. That's where all the action comes from. The action comes from the homogeneous solution. The particular solution is kind of boring. It's the steady state. It's like the growth stuff we were doing last semester or last year, right? This is where the action is. The business cycle is going to come from the homogeneous solution. But to do that, we need to know that it's going to have that form. It's going to look like my famous characteristic roots raised to the power t. This is a little bit technical, but it's actually kind of interesting. Kappa 1 and kappa 2 that look like k's, those are constants. But this function of time means that it's a special function of time. It's the root raised to the tth power. Okay? And there are two of them. That's because it's a second order difference equation. There are two components that you add those together, and we just need to find out that combination, that combination of kappa 1 and kappa 2 that gives it. But we also need to find out what lambda 1 and lambda 2 are. But I told you what those were. If I tell you what the alphas are, you can tell me what the lambdas are. Okay? Man, must be a demonstration outside. A lot of action. Yeah? Yeah, that's one way of thinking about it. Exactly. That's I was hinting at. I don't want to push it too hard because it's true for any system. You know, it's true for any model. But in this particular application, yes, it's the output gap, the relative to the trend that we're not trying to explain in a business cycle. We're really trying to explain the cycle and not the trend. We've already kind of explained the trend. Step 3 is the hard part. You have to find the lambdas. Now, I told you what alpha was, alpha 1 and alpha 2. You should be able to tell me what lambda 1 and lambda 2 are. And to do that, you're going to have to get your pencil and solve an equation. Okay? And that's what they look like. That's called the quadratic formula. Because once you take the definition of lambda 1 and lambda 2 in terms of alpha 1 and alpha 2, and you try to solve for it using algebra, you end up having a quadratic equation. Lambda squared plus something times lambda plus some constant equals 0. And you got to solve for that. And in high school, depending on whether you went to high school in the United States or in Germany or in some other country, if you went to Turkey, you probably learned the German way. There's a different formula, but it's the same answer. It's just a different, the Germans call it the PQ formula, and the Americans call it the ABC formula. I'd love to write this down because this is like the drama. The drama is important. So A times x squared plus bx plus c equals 0. Now, when I was in high school, I was in 9th grade, I learned how to solve that problem. What is x? A is a constant, B is a constant, C is a constant. This is a quadratic equation. This is like bread and butter in economics. But, you know, we're pretty close to that already, but it's going to be involving alpha 1 and alpha 2. You can do it in this section, but what's the answer? Who wants to give it a shot? Yeah. You're so close, but you're not quite there. You started on the wrong foot. No, he was right. It's got b at the beginning, but it's a minus b. Minus b, plus or minus, because b squared minus 4ac divided by 2a. Very good. Okay, there it is. That's the famous, infamous quadratic formula. You have to learn this. Why? Because that's the only way you're going to figure out what lambdas are. It's the only way you're going to figure out what lambdas are. I told you what alpha 1 and alpha 2 are. You got to figure it out. But this is already kind of interesting. Look at this. Remember I told you the solution, this homogeneous solution is powers of lambda. So you already have, if you have some intuition, if lambda is greater than 1 in some sense, in some expanded sense, we're in trouble. That thing is going to blow up. So we want the lambdas to be small in some well-defined sense. Because we're taking powers to t, and as t get bigger and bigger, the powers of t of something that's greater than 1 are going to get really, really big. And that's not what we want. We want the model to kind of damp down to something, to converge. So that, if in a sense, the size of lambda 1 and lambda 2 are essential, and that's why I keep harping on that. And when I say the size, I mean the modulus. Because sometimes, if we're unlucky and this thing is negative, we're going to have a complex conjugate number, plus or minus something times I, right? And that's, don't worry. It just means that the impulse responses have a cyclical cosine-sine pattern, okay? All you have to remember is that when I solve for the lambda, I'm going to get something like this. And it's going to be potentially complex conjugate. If b squared is greater than 4ac, then it's going to be real valued. But if it's not, I can't deny its existence. It means that a shock is going to have a cyclical adjustment. So that's the cookbook. And we will spend some more time thinking about this. If you take any advanced courses in macroeconomics, you're going to have to worry about the stability of a system. And it's going to involve these things, which are in a matrix setup, are called the eigenvalues. The eigenvalues of the dynamic system. So if you don't like macro, you can run away from macro. But if you want to deal with macro and grab it, you're going to have to deal with eigenvalues. So this is kind of an easy introduction to the stability of dynamical systems. So some of you may want to run away right now, but you can't run away from this course because it's required. But otherwise, think about it. Macro is about dynamics. We need to understand that. Yeah?
One question for the second step where we got the output gap in the end. I think on some previous slide you said that the YT is already like in the AD form, it's already the output gap.
Yeah.
I'm wondering if we
Yeah, there's a
the output gap and when we do the output gap of the output gap or?
No, it's a good point. I mean, it's a notational issue. I mean, think of YT now as describing output that we actually put our hands on. Okay, so and then it's got this YP, which is a permanent part. It could be a trend. It could also be time dependent. So in fact, the advanced approach would be to allow the YP to have a growth component, but you have to strip that out first. Okay, so this is, yeah, it's. That's why I think I told you last time that I like to put the hats on, and I didn't do that. But if you like, you can think of YH as being Y hat. Okay. Okay, so you can write the solution to this difference equation as literally as the sum of a particular solution and the homogeneous solution, and that's what I've got here. The first part, epsilon 0 divided by something that's less than 1. We knew that. And then plus this stuff that depends on time. There's no lag values in there anymore. We've actually solved the difference equation. That's the solution. So if you like, that's kind of an important achievement for the day. We were able to write YT in this form. Now, you're probably asking yourself, where do these guys come from? Where do the kappas come from? The kappas are just constants, and they depend on the initial condition of the system. So if there's a period 0, there must have been a period -1, one period back, because the dynamic system always kind of marches forward, but you can always go back and say, what happened before that? And there is no beginning of time here. You just have to define the beginning and then ask, okay, well, 2 periods before that, what was life like? And then if I know those two, I can actually solve for kappa. Kappa 1 and kappa 2 are functions of those initial conditions. That's just to mention it right now. You might be interested later. Okay? Let me just tell you what this means. This has incredible implications. So we've written this like this. We know we have to look at the lambdas. These are called characteristic roots of the difference equation. And this is worth staring at for a second. We see that we're not really sure what lambda looks like. We know it could look like a normal number. It could look like a complex conjugate number if we're unlucky. But actually, if we're unlucky, we may be lucky because we learned something, and we also may have some unusual dynamics. We may have waves, okay? In the more advanced PhD level course, we'd actually talk about that in detail. I'd ask you to talk about the trigonometric identities that give rise to that. It's not worth it. The important thing is that it does imply cyclical behavior. And the reason I know that is because if it's complex conjugate, I can write that complex conjugate number as h plus vi. I is the square root of -1. And that's what makes it so crazy loco, right? But Descartes and Euclid were clever enough to say, well, I can still think about these numbers, even if I can't imagine them. I just put them in a two-dimensional plane. In the horizontal plane, I've got the real part, the horizontal dimension, the horizontal axis, and the vertical axis is the imaginary part. It's that easy. So I've expanded my mind. I can think in complex terms now, because if I get off the x-axis, I'm in the complex world. I've got a complex dimension to my number. So if the solution to this problem involves complex conjugate numbers, I'm going to have 2 of them, and they're going to be mirror images of each other around the x-axis, those 2 dots. If the complex conjugate If the number is real valued, the imaginary part is 0, then v is 0, and then we're on the x-axis, and it's uninteresting. Okay? So just allow me to do that. I take the lambda, I tell you they're going to come in pairs because we live in the real world, and the real world has only complex conjugate pairs as solutions to this equation. So one is going to be the reflection of the other around the x-axis. Okay? That's why I say symmetric about the x-axis. Now, why do I have this circle here? What's the point of the circle? It's a unit circle. It's a circle of radius equals 1. Why would that be kind of interesting for thinking about lambda? Yeah. Exactly. We want to have a convergence result. Suppose the imaginary parts were equal to 0, then we would be on the x-axis. We want to have those lambdas less than or equal to, or actually just less than 1 in absolute value. So that means on the left and on the right. What happens if we have a complex conjugate value? Well, we have to worry about that, obviously. It turns out if we're inside the unit circle, we're stable. We still have stability. So that distance, the distance to that point is what? Now, see if you remember your grade school Euclidean algebra or geometry. What is the distance from 0 to HV? Parfait. Okay? That's the distance to the origin. That's going to be the stability condition. So even if we have a complex conjugate root, we can still have stability, but the length of this modulus, the distance to the origin has to be less than 1. I'm going to show that in a second. It turns out this is because when you have a complex conjugate number and you write down this powers of the complex conjugate number, it's like a cosine curve. So the cosine curve has to be damped, and the distance has to be less than 1. If it's not less than 1, it's not going to be damped. It's going to be either cycling forever, or it's going to be cycling and exploding. Okay, so that's kind of a radical tour de force. You know, getting through this it's just about computing the distance to the origin, and because it's symmetric, those distances are equal. I only need to do it for 1 because they're the same. 1 is above, 1 is below. The distance to the origin is the same. Okay? That's why, and this is called the modulus. The modulus is like an expansion of the idea of an absolute value, but it's an absolute value for a number that's complex conjugate. Think of it as the distance. Okay? So this is called the modulus. The length of the Euclidean distance, or the arrow. Now, if you really like this stuff, now if you remember trigonometry, you can express HV as a distance and an angle, right? If we're going to blow our minds, we might as well just really blow it up, right? So we can use sine and cosine to think about the same numbers. You tell me HV, I can tell you R theta. I can compute it. I just go to my calculator and figure out what's the cosine sine of theta. It's defined as the run over the distance r, or the rise over the distance r. Those are the definitions of sine and cosine. This is going to give me my ticket to getting cyclical behavior. Because if I take this way of writing the complex conjugate number, I can also write it a third way in the Euler form. And if I take powers of that, powers of r times e to the I t theta are just powers of that, which are effectively powers of RT, and powers of something that is cycling over time. So it turns out that that's the second line basically shows that that's just a function of cosine and sine. It's a shifted cosine function. Stability will only depend on r. R has to be less than 1. And r was what? R was the distance to the origin. So powers of that have to be shrinking as t gets bigger and bigger. Okay, so I summarize. This is what we got. The lambdas can be expressed. They may be complex conjugate numbers, and if they are, we can still think about them as being powers of numbers that are real valued in the end. And I can prove that if you want, but it's not really necessary. You end up getting a shifted cosine wave if we have complex conjugate numbers. Otherwise, we get something that's damped over time and goes to 0. There were some questions. Somebody had a question? No. Yeah.
So if some economy is closer to 0, when now talking about R, so it is much safer than the one which is closer to 1. With 1 is 0.9 and 1 is 0.2.
The answer to that question is the closer you are to 1, the more persistent the dynamics are. It's a great question. So if in the limit, if r were very, very small, if we were very close to the origin, then the dynamics would be very, very uninteresting. They wouldn't be persistent. But the solution, if r is very, very close to 1, that means that a shock will take a long time for it to die down, for it to damp down. And that's exactly why we stare at these lambdas, because we care about the persistence. We want a model that gives persistence that looks like the data. And if you look at the standard recession, it takes a while for the recession to go away, right? Like the one we're about to have right now. It may take 6 to 20 quarters, depending. And that, again, these are all things that we can learn from looking at these models. Okay. So I'm trying to, I don't want to spend too much time on this, but this is extremely important. If you take what I just derived and write it in terms of the sine and the cosine functions, you end up getting something like this. So kappa 1 and kappa 2 could be complex conjugate, but kappa 1 and kappa 2 with primes on them, written as the sum and the difference of the original kappa 1 and kappa 2, those are real numbers. So you don't have to worry, we're not getting a complex conjugate, data, we're getting real value data, but they come from this solution, which could potentially lead to complex conjugate numbers. And I've already said we need R less than 1 to have damped oscillation. So again, if you this is not exam material, but if you really care about this a lot, then you can actually use this. Again, this is reacting to a single shock, a permanent shock. You can see that we can derive an amplitude, and the amplitude gets smaller over time if R is less than 1. So it's a damped oscillation in the case that we have complex conjugate roots. You can think of a shift, a phase shift, and you can think of a frequency. So if you let the shock play through, how many times does it cross the origin in a period of time, in a year, 4 quarters? Okay, so this is just some extra information for you in case you're interested. So this kind of shows the one-to-one correspondence between what we call the frequency domain and the time domain. And if you do a PhD in macro or in economics, you would spend some time thinking about that. More complicated, because we can use many methods that are used in applied physics, for example, to look at business cycles, to look at cycles in financial data and the like. Okay, so this is, if you have complex conjugate roots, you'll have something like this. A one-time shock could lead to cycles, and they would lead to cycles forever if R is equal to 1. This is a particular case. This is not going to happen but in principle, it could happen. So this would be the case of no damping. And if you're interested, you can use MATLAB or Excel even to generate examples of a cosine sine function and change the frequencies, etc. Okay, so let's conclude this discussion, and I'll give you some summary remarks. It's important to think about macro as a set of stochastic difference equations. It's kind of what we talked about last week with Slutsky. There's an initial shock, and there's a culmination of that shock's effects. And if we have many shocks, Slutsky said there wasn't just one shock, every period there was a shock. And what we're observing is an irregular set of movements of the economy, but they have the cyclical component, and that comes from the culmination of these shocks. That's exactly what we'd have here. What I discussed before was a single shock, the reaction to a single shock. Okay, and the question about persistence is very good, because if the closer the underlying model tells us we are to the unit circle, the more persistent the shocks are going to be, the longer it's going to take for the economy to digest the shock. So even without the complex conjugate story that I had before, you can still have cycles, and they'll be irregular. We saw that in the case of the AR1. If you shock the AR1, you're going to get something like a cycle. It doesn't look exactly like what we would call our cycle. Everything I'm going to do in the next few weeks will be trying to figure out the most reasonable economic model that gives us this type of behavior. Again, as simple as possible, but not too simple. And again, this ultimate question will be, how persistent are the shocks? How long-lasting are the shocks? It's going to be asking about the size of the roots. So again, how big is this guy? If it's close to zero, then shocks are not going to have any persistence at all. Please remember this cookbook. Okay, you can do this in a lot of different contexts. A lot of you may end up doing microeconomics, dynamics of industrial organization, or you might do econometrics. If you're doing time series econometrics, this is bread and butter. Do a lot of this, okay? And remember this formula, please. Okay. So what does this mean for us? The last 10 minutes, I'd like to get ready for the next week. We're going to talk about a real economic model that is not baby undergraduate ASAD. We're going to actually do something serious, okay? But it's always going to be recurring thought in our heads. We have to think about this implications for dynamics. If we write this down, okay, and we have the characterization with the roots, etc., we study those characteristic roots, we know where they are. I did an example for you so you can calculate it yourself. These are two roots that actually have no imaginary part. They're just real valued. You can also have that, okay? Let's go back to our model again. Last time ASAD, after that AD, okay? AD curve, AS curve. Now I've done the substitution for you. You can write this in a matrix form. And this is what you would do if you took Professor Reinke's advanced course, for example, or if you took, there are many courses on monetary fiscal policy in Berlin that you could take. You can write down, instead of writing everything in terms of y and yt minus 1 and yt minus 2, you can write it in terms of just y and pi and y minus 1, yt minus 1, and pi t minus 1. So a first order vector valued autoregressive system. It contains the same information as before. It's actually a much more elegant way of writing it, right? You don't have to have all those ugly quotients, but it's the same information. It's expressing the same thing. But now I'm putting the inflation equation directly into the object of interest, which is this vector yt pi t. Does everybody understand that? So I've captured the same information that I had before in this ugly AR2. Now I've got it in an AR1, right? This is kind of, and again, the same information should tip you off. Well, maybe it's better to do it like this. Maybe it's better to do a matrix representation. And you're probably right. Why should I force myself to focus on a single variable and write it in terms of this nasty, look at the demand and supply shock. They don't even look as ugly as before, right? They're still there, but they're just, how did I get from one to the other? It's easy. I can just try to solve this. I can invert that matrix. I could even use the lag operator if I wanted to, right? In more advanced macroeconomics, you do that. You can write the vector yt and pi t as a function of lagged values and the shocks. So all I've done is just write it a different way. It's the same information as we had before. Okay? And if I'm willing to invert that matrix, because if you look carefully at this, and those of you who are a little bit mathematically inclined will remember, I've got to invert a matrix to make this work, because when I started with this system. I had a matrix on the left-hand side hitting the contemporaneous values of yt and pi t, and the right-hand side I have a matrix hitting the lagged values. So to write the reduced form, I have to invert the left-hand side matrix, and assuming it's invertible, I can pre-multiply both sides and write the whole thing as a form like this. Okay, so I could also use the lag operator. I could use the lag operator on a vector. That works too. I'm not going to do it for you. I did it last time I taught IAMA, and I almost had a revolution. I just wanted to demonstrate that it gives you the same result. And you should just remember that. It gives you the same result as we had before. Okay? But the ultimate thing you should remember is we've got the impulses and we've got the propagation. We've got exactly the same message, except now I'm tracking inflation as well. I've got inflation as well on the left-hand side. The eigenvalues of the matrix A0 are the same ones as the characteristic roots as before. So they're going to give me the same stability information, even though it's only regarding y and not pi. Now I've got the system, and it's all about the stability properties of that system. So ultimately, that's a message to you. If you go on to do more advanced stuff, you're going to think about the eigenvalues of a matrix, but it's the same logic as the characteristic roots of a univariate representation. Okay? You have a question? It's a matter of taste to call them one or the other. I mean, I would prefer not to call them structural shocks, but there are people who, at some level they are. We're making a structural assumption because the supply shocks involve producers and workers, and the demand shocks involve households and investment decisions by firms. So they are almost, they have a structural flavor, but the purists might say not structural enough for my taste. Maybe I want to distinguish demand shocks coming from consumer financing access versus the central bank policy, interest rates. So, for me, they're structural. For the ASID, they're also kind of structural, right? Okay, so we talked about the characteristic roots. This is just a general set of remarks. You need to pay attention to this in a longer run sense if you care about macroeconomics. There are lots of other details on these eigenvalues, especially regarding their distance to the origin. So going back to this, the eigenvalues will have potential complex conjugate form, and if they do, you need to take their distance to the origin as a measure of stability. Last few minutes, talk about expectations. So we talked about core inflation, the anchor for the AS curve, right? That's the way I tell undergraduates the story, is that inflationary expectations proxy for a lot of other things that are going on, and explain that the Phillips curve could have been stable for some period when people had stable expectations of inflation, but as soon as those expectations become unhinged, then the Phillips curve starts to move. That's the standard macroeconomic narrative. And everything is based on how those expectations are formed. So I try to draw a picture for you. This is the same picture I showed you yesterday, last week. Okay, positively sloped aggregate supply curve, negatively sloped aggregate demand curve, and now I'm putting pi bar there. That's the central bank's target inflation. So I'm trying to make it more specific. And this is a system and a state of resting, a resting point in the system where people expect inflation and they expect correctly inflation. So I know that because the AS curve intersects the LAS curve and the AD curve at inflation that they expect, which is pi tilde. So that's the resting point of the system. This could describe the world in 2017, where inflation was low, we had no pandemic, demand was pretty stable, people weren't talking about Ukraine, we weren't talking about much of anything. Okay? So now what happens if the central bank suddenly says, to hell with that, we're going to shoot for 5% inflation instead of 2%? Just a thought experiment. Okay? And suppose people didn't get it at first. So they wrote contracts expecting 2% inflation, firms deliver expecting 2% inflation, they mark up on that, and then all of a sudden we get this big surge in demand coming from a permanent increase in the central bank's inflation target. This means that the central bank reduces nominal interest rates and stimulates the heck out of the economy. Okay, we've seen this happen in the past in various places in the world. I'm not going to comment on it, but this is when you can think of. What do you see? You see an increase in output, so you see a boom, and you see an increase in inflation depending on the slope of the aggregate supply curve. Now, is that a resting point for this system? Who are the losers after this happens? Anybody? Who are the losers? Somebody must be, I mean, we have this big expansion of output, inflation's rising. I'll give you a hint. People were expecting inflation equals pi tilde. And they're kind of stuck there. They wrote contracts, they agreed to wage increases based on an old, incorrect inflation rate. So that cannot be an equilibrium. That cannot be a resting point for the system going forward if the central bank continues to target inflation at a higher rate. So what do you think is going to happen next? Again, this is undergraduate pictures. Somebody made a mistake here, right? I mean, all the people who expected pi tilde inflation, conditioning the position of the AS curve, they worked harder, they produced more, they may have raised their prices a little bit, but not by as much as we're going to expect in the long run. So what happens next? People, yeah. Yeah. Very good. Okay. I mean, it's a no-brainer that if people continue to observe this higher inflation, they're going to adjust their expectations. So we had this Mickey Mouse equation for core inflation in the model. Part of the people get it right, and some people get it wrong, but eventually everyone's going to figure it out. And those people who didn't get figured out earlier are going to lose. They're going to lose real purchasing power because they can't catch up what they had before. So we'd expect the long run, if the central bank continues to target a higher rate of inflation, we're going to actually have a higher rate of inflation. The central bank is going to do what it's supposed to do. And people are going to figure that out. And they may be mad. They may actually try to get even more. So the dynamics could be a circle, a loop around that long run. It may not be a monotone convergence. So the way inflationary expectations react is going to determine the characteristic roots of the system. It's going to be part of the story. That's why it's relevant what I'm telling you right now. So how we adjust to an inflationary surge, a mistake because policy changed, means that the dynamics of how we get there could look like this. Could look like this. It could, if people are really, really smart and figured out right away, hey, they're just trying to screw us. I'm going to expect 5% inflation immediately. Then this curve shifts immediately, and we get a much more direct movement to the new steady state. So that's why inflation expectations, especially now, right now, what do workers think is going to happen? Do they think the European Central Bank is going to accept a higher rate of inflation for the next 5 or 10 years? They keep saying 2%. Have they proved it? Have they done what they would actually have to do to fight inflation? If they really wanted 2% inflation, we'd have much higher interest rates right now. So now I'm getting real with you. Think about it. So that pi tilde is the most important part of this model. How do workers and firms adjust their expectations of inflation to changing events? Do they believe the central bank? Central bank promises 2%? I don't think so. How much time do they think the central bank is going to need before they react? That's where macro gets really interesting. We call this the question of whether expectations are rational or not. So I'll stop in a second. Rational expectations is still one of the driving revolutions in this field. Do we assume people are really smart? Do we assume that they're stupid? Do we assume they can correct their mistakes? Because obviously it makes a difference. It makes a huge difference. So the rest of the course is about thinking about that. And you'll see that next time we meet, okay? I don't like to assume people are ignorant. I don't like to assume that economic agents don't get it. I think they're pretty smart. The wisdom of the crowd. So keep that in mind. One of the key shocks for us is going to be how an economy works through a mistake, how long it takes for it to happen. Keep that in mind. Okay, sorry I tortured you with the characteristic roots, but it's important, believe me. And Leopold will go through it in section, and you'll have to solve, you'll have to work through this macro model, this baby toy ASAD model with that in mind. Okay, have a nice week. See you next time.